specialty is in dynamical systems and ergodic theory. The ergodic already the title. He has published over 100 papers, and he authored a book about chaotic dynamical systems. That's his book with his colleague, Professor Boyaski. And that book has been the standard book in chaotic dynamical systems. So when I studied this topic, whatever paper I read, always this book was referenced. So I wonder who was Pawel Góra, Professor Pawel Góra. I cannot believe that he's here. So we'll talk about ergodic properties of maps.
It's a pleasure to be at your very nice university in a very nice city. Okay, so I will talk. Do I need the microphone? Or?
You can turn it off.
Is it okay?
Yeah.
Yes.
Okay. It's better. Okay, so I'll talk about ergodic properties of maps. I'm not, okay, it will be a bit technical, probably. Okay, so let's see. So we first talk about measure preserving transformations. So I will give mostly definitions. Yeah. And then on other topics, yes, we will go through this, hopefully. Okay, that's the thank you page. I thank you, Dr. Lee, for invitations. Okay. So as you can see, in this theory we consider a space, which is a measure space. Yes, so it has a sigma field, sigma algebra of sets, which are called measurable sets, and some measure. Yes, and transformation is called measurable if preimages of. Do I have some pointer or to point? No. No, I don't. Okay. So my finger. But as you can see, transformation is measurable, which means that pre-image of any measurable set is also measurable. Yeah? Okay, it's very technical stuff. Because there are some sets which are not measurable and they are very bad, so we cannot measure them. You know? Measure means that we can say what the measure is. The measure is a generalization of length or volume. You know? And at the bottom we have definition, what it means that a transformation preserves measure mu. Yeah. For any measurable set, we want the preimage to have the same measure as the set itself. So, yeah, maybe I'll shoot. Do we have some marker to write this? Right, this is a one. Oh,
Okay.
maybe I'll give an example because without example. Is it visible? point, which is 1/2 1, yeah? And another like this. So this is a transformation. It's a function. Yes, x goes to either 2x or 2 minus 2x, depending on whether the x is sort of smaller than 1/2 or larger. So this is enough. It preserves the back measure. Okay, let's say this is a set B. What's B? What's the preimage? Yes, we have to look what points go onto this B. So this is one part of the preimage, and this is another part of the preimage. Yes, B1, B2. So we see from this picture that preimage of B is B1 plus B2. The slope is 2. Yes, the derivative is 2. So if this has some length, this has half of the length. And also this has half of the length. So we see that if this is some measure A, yes, the measure of this, okay, I should not write this. So say measure of this is A. So measure of B is A. Then the measure of this is half A. So measure of B1 is half A. And measure of B2 is half A. So together, the measure of the preimage is the same as the measure of original set. So this is an example of measure preserving transformation. Another one is a rotation of the circle. Yes, say this is a circle, and we rotate by, say, through some angle alpha. So this obviously preserves length, yes? If we have an interval here, say B, preimage will be, this will be tau inverse of B. It's obviously the same length, yes? So it preserves the measure, the length of the circle. So these are two examples of measure preserving transformations. As you can see, they are very different. And they really very different. Yeah. Okay. So now we know what a measure preserving transformation is. Why we're interested in measure preserving transformations? In many systems, what is interesting for us in science or in everyday life? We're interested in the future, yes? If you can predict the behavior of stock market, you can be rich, yes? Even if you can predict something simpler like weather, it's beneficial to you, yeah? If you know if it rains tomorrow or not, you change your behavior, yes? So it may be important. It happens that many systems are not predictable. For example, the weather. As you perfectly know, they tell you what will happen tomorrow and they tell you that it will rain, but it doesn't rain. Or, even worse, they tell you that it will not rain, but it rains. Yeah? Okay, so for such systems, the precise prediction is not possible. That's why we use this invariant measure for the prediction.
We don't say what will happen, we just say with what probability something will happen. Actually, they give you this in the weather prediction. They don't say it will rain. They say that probability of raining is 20%. Yes, usually. At least in my town, that's what they do. So this is an example of this using measure, invariant measure, as a prediction. Because they don't know what will really happen, but based on statistical information which they collected from the past, they know what is probability of different behaviors given state at now. Yeah? That's how the weather is predicted, for example. Okay, so this is invariant measure. It gives you some prediction for the future. If you know invariant measure of some system, you can say that with some probability it will behave in some way. So that's why this very abstract notion is useful, can be useful, if you find it. Okay, so, but what I will go now, it will be very abstract, not related to the weather in any way. Okay. So this is the story about invariant measure, and that's an abstract theorem which says that we don't have to check if it really preserves measure of all sets. It's enough to check for specific sets. Yes, for example, if we're on the interval, it's enough to check for all sub-intervals. So the very complicated measure, very complicated algebra of all measurable sets is reduced to the family of simpler sets, like intervals. Okay. So this is just useful theorem, a tool for checking the invariant measure. That's what I did here. Yes, I didn't consider a general measurable set, which can be very complicated. I just checked that for an interval, the pre-image is really of the same measure as the original set. Okay. That's another tool how you check that the measure is preserved. It's enough to check that the integral for any bounded function f, the integral of the function and integral of the function composed with the transformation are the same. Yes, instead of checking the measure for the images, it's enough to check if the integrals for some function are the same. If the space is compact, it's enough to do this for continuous functions. Okay, so this is a more general example of the measure preserving transformation. So here we have two branches. In this example we have R branches. So this is another map preserving Lebesgue measure. So say 0, 1 to 0, 1. So say 1, 2, 3, 4, 5. 5 pieces, yes? So the 1, 2, 3. So if R is 5, the map looks like this. 5 branches. So the proof is the same. You just take an interval and take preimages. Each preimage is 1/5 of the length of the original, yes, because the slope of these lines is 5. There is 5 lines, 5 preimages. This is rotation described differently. Okay. Now, this is a very general theorem which gives you existence of invariant measure. That's Krylov-Bogolubov theorem. It's very old, 1937. So it says that if we have a compact metric space and tau, the transformation is continuous, then there exists an invariant measure. Yes, that's a general theorem. So, 2 important assumptions: the space is compact and transformation is continuous. So below it's the proof of this theorem, which we maybe will not go through. So, on one hand, it's very interesting theorem because it gives you, in very general situation, existence of invariant measure. But on the other hand, it doesn't give you any information about this measure. So very often you may just get an invariant measure which is 1 point measured at some attracting fixed point. So this is on one hand it's very general, and on the other hand it's too general. It doesn't give you concrete, interesting information. But it's a good base for other studies. Okay. So another interesting fact about measure preserving maps is this thing famous Poincaré recurrence theorem. It's also very old, older, 1899. So it says the following. We have a measure preserving transformation. If we had a set of positive measures, then almost all points of the set return to the set infinitely many times. So this is recurrent, yes? Almost every point from the set, after some time, will go back to this set. And again, and again, and again. Infinitely many times. So this means that if we have invariant measure, the points don't go somewhere, they go back, return. So this is kind of beginning of chaotic behavior, yes, because they will. Non-chaotic behavior is like a flow. The points go into some definite direction. Yes, chaotic. They go and go back. Go and go back. So there is some mixing of the space. So this is Poincaré recurrence theorem. We have the proof, but I skipped the proof. This is, I was not sure what the public will be. Yes, so I probably prepared too much material and maybe too precise. Okay, but let's look at this interesting corollary of recurrence theorem. Yes, the map which is written on top, tau equals 10x modulo 1. So this is a map which looks like this but has 10 branches. Yeah. So this is a map which is used decimal expansion of number. Yes? How you expand a number into decimal. You just use this map 10 times x modulo 1. Yes, so if you have x, which is written there, that's decimal expansion of x between 0 and 1. So it's epsilon 1 over 10, epsilon 2 over 100, epsilon 2 over 1000, and so on. Yes? If you do this map, 10 times x modulo 1, the first epsilon 1 will be an integer. Yes? You will multiply this by 10. So the first 10 becomes epsilon 1 and it's an integer. So modulo 1 it will vanish. So the image is this after applying. So we know that this transformation preserves measure. So in particular, recurrence theorem holds. Yeah? So let's look at this set. So this is a set from 0 to this number with some fixed digits, epsilon 1, epsilon 2, up to epsilon n. This is a piece of interval, yes? So it has positive interval. By the recurrence theorem, it means that almost every point will return to this interval infinitely many times. So what this means? This means that this group of digits is present in the decimal expansion of almost every number infinitely many times. Because almost every point will return to this interval infinitely many times. So these digits are infinitely many times somewhere in its expansion. So this is a corollary from this. For example, if you consider a set of numbers in 0, 1 which don't have digit 2, the measure is 0. Yes, if you prohibit 2, any digit, you will get measure 0. If you prohibit any 2 digits in, yes, say 1, 2, also that. In this theorem says that if you prohibit any finite sequence of digits, then you get a set of measures. Okay. So what we're going to talk about is about different kinds of being ergodic, of being causal. So the first step, the easiest, is to be ergodic. Ergodicity means just that the space is we cannot divide the space into 2 pieces or more on which the dynamics is separate. Yeah. So the exact definition is here. Yes. Yeah. So the map is ergodic if for any b, if b is invariant, this means that the set b is invariant, then either the measure of b is 0 or the measure of the complement is 0. So the only invariant set is set of full measures. Yeah? So this means that the space cannot be divided into subsets which don't communicate. Okay. maybe I'll show you an example of non-ergodic transformation, and this will explain more what I mean. Okay, so that's the diagonal, and we can do something to that. So this can be 0, 1, 0, 1 again, but I don't consider. Okay, so my map will be like this, and say like this. Yeah. So as you can see, any point from this interval will go back to this interval. And any point from this interval, it's actually here, will go back to this interval. So this is non-ergodic transformation, yes? It has two pieces which don't communicate. So the ergodicity is saying that the situation like this doesn't happen. Any invariant set is either a full measure or zero. So this is the weakest form of being chaotic. Yeah? Okay. So here I prove. I prove that the map, which is similar to this one, but 2x. This map 2x modulo 1 is ergodic. The proofs of ergodicity are usually difficult because they have to go down to basics. Okay, so here we more or less prove it for every interval of binary interval and then approximate arbitrary interval. Okay, I will not go through the details of this maybe. So we have different theorems which give equivalent conditions for ergodicity. Yes, so tau is ergodic, so we have three conditions. This is symmetric difference. The delta defines the symmetric difference, which is defined at the top. So it's A minus B plus B minus A. So it's the difference between the sets. Here, this is already sounds like a mixing condition, yes? For any sets of positive measure, for at some point in the future, or in the past actual, privilege of A intersects set. Okay, so if we have any two sets of positive measure, some frame image of one has to intersect the other. Okay, so that's another theorem about equivalent conditions for ergodicity at the top. Yes, so tau is ergodic, or we can say it using functions. So for any measurable function, f and f composed with tau is the same. Sorry, no. This would be just preserved everything is almost equal. And the third condition says that it's enough to check it for L-square function. That's some extra theorem which says that we have compact space and invariant measure which is positive on every open set, and tau is continuous, then the set of points whose trajectories are dense is of measure 1. So this means that almost every point has dense trajectory. Trajectory is the set of images. Tau of x, tau second of x, tau third of x. Now this is something similar to Poincaré recurrence theorem, which is called Katz's lemma. It's proven in 1947, so it's also very old. Okay, so it says that so this formulation is most interesting. This is the time of return. Yes, the recurrence theorem says that almost every point returns to set A. Yeah? Now n is the time of return. So if it returns after 10 steps, then n of x is 1. And the lemma says that integral of the time of return is equal to 1 of mu of A. So that the smaller the set, the longer the time. Yes, on average. This is average of the time of the return. So average time of return is 1 over the measure of the set. So it definitely tells you that it will return many times. Yes? And so this is a natural. You probably know something like this from Markov chains. Yes, it's Markov chain is also an example of a measure preserving transformation on finite space. Yes, so the waiting time to achieve some state is equal to 1 over the measure, stable measure of the state. Okay, so this is Katz's lemma. It's stronger version of Poincaré recurrence theorem. It's good for ergodic transformations. Yes. Recurrence theorem was in general if there is an invariant measure. Again. So now ergodic measures have different interesting properties. So for example, here we see that if we have two ergodic measures, they have to be mutually singular. So they which means that there are like two pieces of space. First measure is on one piece, second measure on the other. Yes, so singular measures. Sometimes the measures can be singular, but their supports may intersect, but this is more complicated situation which we will not discuss. Okay, so two ergodic measures are either identical or singular. Now, another interesting property of ergodic measures is that they are extreme points of the set of all invariant measures. The set of all invariant measures, you can think about the space of measures on some space, and among them consider invariant measures for some transformation. They form a set, and the extreme points of this set are ergodic measures. Extreme point, finally, dimensional case, if you have for example, a triangle, extreme points are the vertices. Yeah, if you have pentagon, this is pentagon, yeah. There is 5 vertices, these are extreme points. Extreme points of the circle are all points of the circle, because they are all extreme. Yes, extreme means that it cannot be a combination of 2 other points in the set. So this happens with, yes, now the space is infinitely dimensional because it's a space of measures, but the definition is the same. The extreme point is a point which is not a combination of 2 other points of the space, of the set. And ergodic measures are extreme points of the set of all invariant measures. So this is this may be interesting in some theories. Yeah. Okay. So I'll skip a few. Okay, so maybe I should say this, what is a recurrent set? Yes. So the point, as you can see there, yes, the point X is called recurrent if and only if X belongs to its accumulation point. Accumulation points, omega of X, are the omega of X are the limits, partial limits of the trajectory. This is the definition. So recurrent points are partial limits of the trajectory. So there exists an infinite number of points in the trajectory such that they converge back to X. So it's kind of there exists a sequence of their images which converge back to X. So it's recurrent. Yes, they go back. Okay, so the theorem which we have here says that every invariant measure is supported on the set of recurrent points. Yeah? So the measure, if mu is invariant measure, this theorem at the top, then the measure of the complement of recurrent set is 0. So almost every point is recurrent. Okay. So now an important, probably the flagship, yes, of all theorems referring to invariant measures is Birkhoff ergodic theorem. Yeah? So it's a
So the physicist would say time average is equal to space average. That's the ergodic theorem. So instead of looking at the trajectory and measuring some quantity f on the trajectory, it's enough to look at the space average integral of f with respect to the invariant measure. So this is Birkhoff ergodic theorem. It's called individual ergodic theorem because it tells something about the behavior of points, just on point. So this is general, without assuming that the measure is ergodic. But if it's ergodic, then we have the f star is constant equal to the integral. Yeah, that's in this corollary. So now we can go back and get an application. Before I was saying that every combination of digits in decimal expansion shows up in expansion infinitely many times, yes, or almost every. Now using Birkhoff ergodic theorem, applying it to the same transformation, 10 times x modulo 1, we can obtain the fact that the probability of probability of seeing, say, 1 in expansion of arbitrary number is 1/10. Yeah? Every digit has the same probability of being in the expansion. So the proportion of ones in almost every expansion is 1/10. Proportion of digit 3 in almost every expansion is also 1/10. Every digit has the same average number of occurrences. So that's what we get from numbers which have this property are called normal numbers, because this was discovered by Birkhoff, by Borel before, and he called numbers which have this property normal numbers. Yes, if every digit has the same probability of showing up in the expansion, the number is called normal. So, although we now, using Birkhoff ergodic theorem, we know that almost every number is normal, we don't know anything about specific numbers. For example, this is open problem. Yeah? If 5 is a normal number, it's not known. So, it's an open problem. That's definitely, if you prove that it's normal or find out that it's not, you will be very famous. Yes? I'm not saying that it will be easy or useful. Okay. Also, there is because this is not this is normal for decimal expansion, yes, but as we saw here or somewhere else, there are different expansions, yes, for different bases. Yes, there are binary expansion, ternary expansion. You can use 12 for expansion, whatever. Yes, so the number can be normal to one base and not
to other weight. So there is a lot of problems related to this. Yes, what's the relation between numbers normal to base 2 and normal to base 3? That's also an open problem. Okay, let me see. So this is another condition for ergodicity. Here, so it looks like already as mixing condition. So we see the soft already. The tau is ergodic if and only if this average goes to mu times mu a times mu b. What this means? This means that on average, in time, the sets tau inverse, tau minus I of A and B, they become independent. Yes? Because the measure of tau inverse I A is the same as measure of A. So this means that these two sets, which are under mu at the beginning, they become independent because the measure of their intersection is equal on the average asymptotically the product of the measures. So this is what chaotic systems produce. Yeah? Two arbitrary sets, when one is transformed with the transformation, they become independent. Okay, that's okay. Another, it's mean ergodic theorem. Sorry, we just said that this average goes to F in LP. Yeah, so that's von Neumann theorem. This actually was proven before Birkhoff ergodic theorem because it's easier theorem. It's just says that the convergence in P norm occurs. While Birkhoff ergodic theorem tells that the convergence is almost everywhere, which is much stronger statement. What we have the proof. Now it's another notion. It's weak mixing. So that's yes. So we have different states of chaos. Yes, of chaos. The weakest chaos is to be ergodic. Then we will consider weak mixing as stronger form. Then strong mixing as even stronger form. And then the strongest is exact. So there are 4 basic forms or steps of being ergodic. So yes. So as you see, yes, we stated before that for being ergodic, this condition at the top is everyone. Now, weak mixing means that this convergence is stronger, yes, because we take the difference and we put the modules. So this is slightly stronger condition, and it's called weak mixing. For example, so I'm not going to prove what I will say, but the example of ergodic, not not weakly mixing transformation is the rotation. So let's consider the rotation through angle alpha, but the angle alpha such that alpha over 2 pi is not rational. Yes? Irrational rotation. So 2 over 2 pi, or pi, is not rational. Then it's ergodic. Yeah, with this it's ergodic, but not weakly mixing. Why is it ergodic? I will not be able to prove it. Yeah, it's easy to see that if this is not satisfied, then it will be not ergodic.